Hello everyone, some BC Calc here on polars. The goal by the end of this set of notes is that you'd be able to work with polar coordinates and kind of understand the difference between polar and rectangular, as well as do some polar calculus. So I'm not going to talk through each of those 6 parts there, A through F, but I am going to talk about them. I'm just not going to read those off. So let's look, for example, at just a triangle. Let's look at a simple triangle in quadrant 1. Oops. Come on now, draw things. There we go. Okay, so we call the origin O. Right? This is the origin, and it is the point 0, 0. Okay, so any point out there, we're going to just call it P. Okay, and it's going to represent this pole, and the pole connects the origin to the point. Okay, and we're going to call it R theta. Okay, so what R is it's different than what we're used to in our world of math, which is rectangular coordinates. So here's rectangular coordinates. We'll get a little bit into this a little bit more in a minute. This is rectangular. This is going to be polar form. Okay, so my mistake, I referred to the segment connecting as the pole. The pole is actually this point right here at the origin. So we typically think of a point in the XY plane as some horizontal movement, and some vertical movement. Okay, so we get there in a rectangular fashion. We travel a certain number of units to the right and then a certain number of units up. So let's say we go horizontally X units and vertically Y units, and we get this point, right? We get this point X comma Y. Okay, polars are different. Polars, we extension, and then we rotate. Okay, so R is some extension, right? So we're going to extend out R units. And then we're going to rotate theta radians, right? So if I extend out R units and I rotate theta radians, I end up in the exact same place. Okay, so extension rotation as opposed to horizontal vertical movement. So what if R is negative? Okay, so let's take the point, for example, 2 comma pi over 4. Okay, let's look at what 2 comma pi over 4 would look like. We would extend 2 units out to the right. Okay, and then we would rotate pi over 4 units, or radians. So we would be at this point 2 pi over 4. Okay, so here's the pole, or the origin, 0, 0. Here's our angle, which is pi over 4. And here is our radius, length of 2. So how would this be different if we were to have a negative R value? So let's go negative 2 comma pi over 4. Recall that any angle that's positive is a counterclockwise rotation. So instead of extending to the right, we'd extend to the left. So here would be a extension of negative 2 and a rotation of pi over 4. So we will get an extension to the left, rotation of pi over 4 units, and we would end up in quadrant 3 for a negative value for R. So let's sketch a few of these polar coordinates. Extension, rotation. Remember, extension, rotation. So I extend 1, I rotate 5 pi over 4. Well, 5 pi over 4, I extend out 1 unit, and I rotate 5 pi over 4. That puts me right here. Where I have a hypotenuse. Well, I don't want to talk hypotenuse yet, but I would have this reference angle of pi over 4 here, right? Because this angle of rotation would be 5 pi over 4. That reference angle right there would be pi over 4. So I could say, this is a nice little transition, but I could say that 1 comma 5 pi over 4 is equivalent in its terminal side to negative 1 pi over 4. Right? Those two would end at the exact same terminal side. I'll label this as we originated, but that would end up in quadrant 3. How about 2? Extension of 2, rotation of 3 pi. Well, that would land us right here. 2 comma 3 pi. Now how did we get there? We extended out 2 units, and then we rotated 1 pi, 2 pi, and then another time around for 3 pi. Okay, so that gets us right on that quadrantal. And in rectangular coordinates, right, if I were to put this in rectangular coordinates, that would be the point negative 2, 0. All right. We're going to talk about rectangular coordinates here in just a minute. Okay, how about example 3 here? 2 comma negative 2 pi over 3. Well, that would put us in quadrant 3. We would extend out 2 units and rotate negative 2 pi over 3. Okay, that would be equivalent to an extension of negative 2 and a rotation of pi over 3. Let's look at that. Extension of negative 2 and a rotation of pi over 3. That would get us to the same place, but the original, of course, was 2 comma negative 2 pi over 3. Remember, extension, rotation. Okay, what quadrant would you end up with if you had an extension of negative 3 and a rotation of 3 pi over 4? Well, you'd end up in quadrant 4. Extend negative 3, rotate 3 pi over 4. That puts us right here. There you have it. Okay, let's take a look at the next few examples. All right, now let's consider the following diagram. You can see that I've got both polar and rectangular labels to this right triangle. Of course, here I've got theta, r, y, and then of course this value here would be x. So a couple of important things is that the cosine of theta will equal x over r. That tells us something important for later on, that x will equal r cosine of theta. Okay, likewise, the sine of theta will equal y over r, which tells us that y equals r sine of theta. And the tangent of theta, let's just stick with that trig world, will be the opposite over the adjacent, which will be y over x. Okay, another item you might have recognized is the Pythagorean Theorem is important here. X squared plus y squared will equal r squared. And of course, in all these situations here, we're dealing with a right triangle, so we may end up seeing some unit circle ratios showing up for us. So let's look at example 5. Of course, these are, you want to pocket all of these equations because they will be utilized later on. Okay, so let's pocket those for a minute and convert to pi over 3, which is polar in its nature. Okay, extension, rotation, to Cartesian coordinates. So that would end up in quadrant 1. Okay, so I like to sketch these as a right triangle because R is the hypotenuse, always will be. Put a 2 there. And this isn't to scale, but this angle would be pi over 3. So if I look at a triangle from the unit circle that we're very used to looking at, there's a unit circle with a radius of 1, right? So I've got a hypotenuse of 1, an angle pi over 3. That would make my short leg, or my x value, 1/2, and my y value, or my long leg, √3 over 2. So now to get to this triangle that I have on the left, I'm going to multiply everything by 2. And what that'll do is it'll give me my x and y values. So my hypotenuse clearly is 2. My short leg, which isn't in this diagram, but should be 1. And my long leg should be √3. So this point, which was the point 2 pi over 3 in polar, has now been converted to rectangular or Cartesian. Okay, those two things are, two descriptions are synonymous. Okay, Cartesian form. Okay, that point in Cartesian form is 1 comma √3. So you can see how the unit circle obviously is helpful here. Let's look at another example. Example 6, represent this in polar coordinates. Okay, so -1 and +1. Okay, so -1 and a +1. Okay, anytime your x and your y value are the same with potential different signs, you know you're going to be dealing with some form of pi over 4. So if I were to use the Pythagorean Theorem, right, 1 squared plus -1 squared is equal to r squared. So it'd be 2 is equal to r squared. And we're going to always, not always, but most of the time label r as a positive. Okay, so that would give me my extension. Then my rotation, of course, if I extend √2, then my rotation will be larger than 90 degrees, right? This will end up being 3 pi over 4. So one polar representation of this rectangular Cartesian point would be √2, 3 pi over 4. Take a moment, pause the video, and come up with one with an r value less than 0. Okay, after you've paused your video, you could also write this as -√2 and a negative pi over 4. All right, so extension of -√2 and then rotation clockwise of negative pi over 4. It's another way we could get to that coordinate in polar form. Okay, let's look at graphing on the next slide. That'll be the end of part 1 for polars. Okay, so example number 7 is asking us to graph r equals 2. Pretty abstract, at least the first time you graph a polar. But if r equals 2, that means that no matter what, our extension will always be 2. So it doesn't matter what our rotation is, whether it's pi over 6, pi over 4, pi over 3, pi over 2, 2 pi over 3, 3 pi over 4, 5 pi over 6, or pi. What you can see is that you're forming a circle. So if r equals 2, there's no dependence at all on the angle measure. That's terrible, but that would be the graph of r equals 2, right? That tells me that x squared plus y squared, right, would equal 2 squared. We said that x squared plus y squared equals r squared. That was from our pocketed identities, so to speak. So what is that? What is this equation? This is a circle with radius, I'm going to try to spell it right, equal to 2. Okay, how about a graph of theta equals 1? Well, theta, let's see, theta will always be in radians. So get used to it. And 1 radian is approximately equal to 57 degrees. Okay, so let's consider one of the potential points on theta equals 1. Well, if theta equals 1, I could extend 2 units, rotate 57 degrees, right? Or I could extend 1 unit and rotate 57 degrees. Or I could extend 3 units and rotate 57 degrees. Right? What you'll see is that we start to form, regardless of our rotation, our extension, our rotation ends up being 57 degrees. Even if we went negative, -1, rotate 57 degrees. -1/2, rotate. What we're getting, right, is this line. And what's cool about that line is that we know, based on what we have pocketed earlier, is that the tangent of theta equals y over x. Therefore, this line is actually the tangent of theta times x. So tangent of theta is the slope of that line. It's kind of cool. And the tangent of 1, I don't know what that is, but that's the slope of that line. It's kind of cool. Okay, let's look at an example of sketching the following curve. Let's start by making a table of values. I'm going to fill in a few values here in a second after I pause the video just to save some time. Okay, so I've got some theta values that I'm going to clearly plug in for theta, and it's going to give me an r value, which will be my extension. So I'm going to plug in the angle of rotation, and I'm going to get out a extension value, which is going to help me create this graph of r equals 2 cosine theta. So let's first take a look at and evaluate the following. So 2 cosine of 0. Cosine of 0 is 1, so I would get 2. So this point in polar form would be 2, 0. So I'm going to extend 2, rotate 0. We'll talk about that in a minute. Okay, cosine of pi over 6 is root 3 over 2. So this would be the point root 3, rotate pi over 6, extension rotation. Cosine of pi over 2 is root 2 over 2. So this would be a root 2. If I multiply 2 times root 2 over 2, I get 2. So my polar coordinate would be extension and rotation. Okay, cosine of pi over 3 is 1/2. Therefore, 2 times 1/2 would be 1. Polar coordinate, extension, rotation. Continuing on, cosine at pi over 2 is 0, so that'll be 0. 0 for extension, pi over 2 for rotation. That'll be an interesting point. We'll talk about that in a minute. Cosine of 3 pi over 4, again, negative root 2 over 2. So I will get a negative root 2, extension of negative root 2, rotation 3 pi over 4. Cosine of pi is -1, so I'll get a -2, extension, rotation. 3 pi over 2 yields a cosine value of 0, so 2 times 0 is 0, so I would have a 0 and a 3 pi over 2. And then finally, 2 pi. Cosine of 2 pi is 1, so 2 times 1 is 2. So I'd have extension of 2, rotation 2 pi. Now let's graph this. We're going to see a pretty cool symmetry show up. Poorly sketched. Let's try that again. There we go. It's better. All right, so our first point. Extension of 2, rotation is 0. So I've extended out 2, and I've rotated 0 radians. Check. Our second point, extension of root 3, rotation of pi over 6. So root 3 is somewhere between 1 and 2, closer to 2. And a rotation of pi over 6. Okay, extension of root 2. rotation of pi over 4, root 2 is just a little short of 1. Rotation pi over 4. Okay, so you can see the rotation at these two values are pi over 6 and pi over 4. Okay, I'm going to get rid of those to save some space. I'm going to continue. Extension of 1, rotation pi over 3. So I've checked these two off. Extension of 1, rotation of pi over 3. Puts us about there. And in our next point, this is an interesting point. I'm going to extend 0, which means I'm going to stay at the pole, and I'm just going to kind of turn in place. So what you'll see so far is that I have formed half of a circle. Now let's look at the other half for a moment. I'm going to extend negative root 2 and rotate 3 pi over 4. So if I extend negative root 2 and rotate 3 pi over 4, I'll actually get, and I skipped a point here. It's not my best point. Let me try that again. Right there. Good. So you can see that I would have rotated 3 pi over 4 degrees to get to that point. Now I skipped this point here to save myself space in the table, but you can see that I'm starting to form this circle. Okay, let's continue. I have sketched that. I have sketched that. Let's go negative 2 and a pi. Now I'm skipping points to save space in the table. Extension negative 2. Rotation pi actually puts me right at this point here, and it helps me to kind of seal in the rest of that circle. So all I had to do was go pi units of, go in my table from 0 to pi in order to complete the circle. Now as I go to other angles, what I'm really just going to do is I'm going to trace over the circle a second time. So 3 pi over 2 would put me back here, right? Extension of 0, rotation 3 pi over 2. So I skipped these 3 points, got myself back here. And then for 2 pi, so 2 pi, I've skipped over these 3 points and I've got myself right back here. So I basically traced over this circle twice. So that's how you graph r equals 2 cosine theta. Now, it's kind of cool, but the 2 here just represents the diameter of the circle. Okay, now if this were to be negative 2 cosine theta, all it would do is flip the circle to the other side. But I think of cosine as like x, so its center is on the x-axis. If you were to have r equals 3 sine theta, you can think of that as a circle with its center on the y-axis with a diameter of 3, right? So this would be 3 halves. This would be negative 3 halves, etc. So that would be r equals 3 sine theta. If you were to make that a negative 3 sine theta, it would just duplicate it on the other side of the x-axis. Okay, so that's a basic on graphing polars. Let's look at one more slide with some important information on it. Okay, a lot going on in this slide. I'm just going to highlight a couple of items. The polar coordinates stuff that we went over and its formulas. X equals r cosine theta, y equals r sine theta, tangent theta equals y over x, and then the Pythagorean theorem. A circle centered at the origin would just come in the form r equals a number, right? And it'd have a radius of that value. A circle on the x-axis would be in the form r equals a cosine theta. So for example here, we have a diameter of 4, which means we have a radius of 2. You can see that circle right here in blue. A circle on the y-axis would be in the form a sine theta. Of course, if a is negative, that would be below the x-axis. If it's positive, it would be above the x-axis. And of course, its radius would be half of whatever the absolute value of that number would be. Okay, a couple items here I'm going to talk about a little bit more in the next set of notes. So leave this for now. That is part 1 of polars. We'll see you guys in the next video.